Welcome everybody to Sustainable River Basin Management, Module 5, Part 2. We have been asking the question of how can we assess sustainability, and I want to present to you this time something about decision support systems. Now, decision support systems are founded on the primary objectives of the overall water management strategy, and those entails the environmental compatibility, the cost recovery of water services, and the coverage of demand for all sectors. Now let's look into the methods of decision support systems. It starts or departs from grouping various monitoring parameters into indicators, but in a slightly different way. So it still requires a monitoring system in place, the monitoring of predefined parameters which are relevant. And those are analyzed and compiled for each parameter in the following way. We want to know the average value of each of these parameters. We need to know the reliability of each parameter. Reliability would be the probability that a criterion value will be within the predefined range of satisfactory values. This satisfactory here has to be defined. It has to be defined within a frame of ecological aspects, ecological functions, also in the frame of cost analysis, in the frame of valuing certain values again, and very much depend on our current knowledge also. And then we have to analyze each of these parameters against its very own resilience. The resilience is an indicator for the speed of recovery from an unsatisfactory condition. That means we need to understand how these parameters actually work under different impact conditions, and we need to be able to identify what is satisfactory and what is unsatisfactory. When are we within a limit or in a range that is acceptable, and when are we actually moving out of that range and reaching a tipping point where maybe resilience will be used up and even no recovery may be possible. And then we have to analyze against the maximum extent in terms of geographical range and the duration. It essentially is building on an ecosystems approach and requires substantial knowledge of how parameters interact with each other, and very often we do not actually have all this information available in complex systems. But that is the basic concept of such decision support systems towards sustainability assessments. Now, this is showing you an example matrix of a decision support systems indicator base. We have basic indicators here. We have the dimensions, environmental resources, the efficiency, and economics. And then we have here indicators which can be determined either by calculating straight away from data, expressing this in a percentage, or by forming out of another subset of parameters an index something like this groundwater exploitation index or the non-sustainable water production index. So this already includes a larger amount of parameters and data which were combined to this non-sustainable water production index. The dependence on interbasin water transfer, for instance, it's not a parameter in itself. It is, again, it's a composition of various parameters, which then takes us to a definition of dependence on interbasin water transfer. So, and then on the other hand, we have here precise values that can be measured and reported, like the rate of cost recovery or the demand coverage versus irrigation demand. Those are measurable parameters again. So this shows us that this is again very complex and can easily become much more complex and intransparent or difficult to understand individually, and maybe quite differing between different applications, different river basins, different countries. The assessment inputs, as an example, including all of the sustainability dimensions and providing balance indicators, which are also measurable, in this example list. We have the environmental resource, social indicators, economics. Those are assessed to versus exploitation, dependencies, the water qualities, pressures, deficits. And then we have various parameters which we can measure, we can obtain from our databases, the social databases, environmental, indirectly we can obtain environmental resources, dimensions, and the economical dimensions and social dimensions from our existing databases. So this is an example where we have on the input side a quite balanced selection of parameters, which then can give us a balanced, a more straightforward assessment result on this side, and a comparison between probably different years and different regions also. Just to move into a very specific example here, this is the GLOBA project, which means global change and the hydrological cycle. This is a major undertaking by various institutions across Europe work together. Various institutions from universities to research centers to state actors. This is dealing with, this is an example of a decision support system for the Danube River. The Danube River is the major river catchment, river basin in Western Europe. And it was the objective of this undertaking was to develop a complex model framework to analyze the effect of global change on the interactions of different components of the water cycle and the overall effect on the hydrological cycle on in the specific case of the example case of the Danube River. The components which were included into this complex model framework included climate, economical development, natural resources, land use management, tourism, population numbers, population migration, water supply, and many, many others. So it's indeed a very complex and cross-cutting framework. and requiring a huge number of background data. So the database network of this system looks in a generic way like this. We have the actor or the controller. This could be a politician, it could be also a river basin organization sitting here, accessing this information and inputting information into it, or taking actions in the way of allocating water or suggesting the construction of a new water treatment facility, for instance, or suggesting certain water priority projects in a region, or the turn down of certain industries because they would have or they do have a very negative impact on water and land in this Danube region. Then we have the link to the different compartments, the atmosphere and the natural components of which control what happens in our atmosphere as one of the water cycle compartments. Then we have our terrestrial component dealing with the land surface, all of the different aspects influencing land surface. That could be soil, it could be terrain, topography, it could be snow cover, the biosphere, our various land uses, specifically agriculture, and so on. So this is our surface system, including the different spheres, hydrosphere or biosphere, land surface, and then we have separated, singled out from the land surface the hydrological component, the river networks, the lake systems as influencing what is possible and what is happening on our land surface, what are the options, and then singled out again our groundwater subsurface water component or groundwater connected directly to our river systems, but treated as a separate subsystems component. So we have the different hubs here and the linkages between those the different compartments and the different human actors in this. Now, this requires a lot of baseline data, as you can imagine, when we want to cover all these different themes or topics that I listed before, and this is just to show you an insight. You can go online yourself and go through this database on your own. Take time because it's very, very detailed and very rich. I just want to provide a clue. This is the catchment here, and this shows just the topography. Then we have various possibilities to visualize various components from population to soil to GDP, groundwater quality, just as examples, the hydrogeology, land cover, and so on, the different water sectors, climate data, the solar radiation, organic carbon in soils, and so on. So all this can be visualized here, and it can also be combined and visualized in a combined manner, where we can already not only visualize in a one-to-one way our baseline data, but by combining various different sets, we can intersect them and create information from that, which helps us to already take decisions. So this is indeed a kind of decision support system which helps somebody who would come from a water background to put together information from the economic sectors, from the social sectors, and obtain additional new information to take on decisions. Another example of this that shows us the level of detail here, we have here the patches of showing us the abstraction per communal administration. This means that in an individual village or in a small town or city, council can use that database and see and zoom into his or her specific jurisdiction and obtain information such as the abstraction in and around that community area, that administrative area. So this is extremely detailed, a very detailed level that indeed can help not just to visualize something, but to take decisions on a local scale. We have, in addition here, combined with this, the abstraction per borewell for water, drinking water supply or irrigation. Again, we have here different classifications of how much is being abstracted per year in cubic meter, and we can see some of the areas where there's a lot of abstraction taking place, some regions, and some where we have less or even white blank areas. Here is not that there is no information, but in this case this means white area, there is no abstraction taking place. So we have areas where for some reason there is no abstraction. It could be a protected area, it could be that those areas are served by some other region. There are pipeline systems, distribution systems serving those areas. So there are probably various reasons for why there is no abstraction taking place in those specific areas here. So important here to take home is really the level of detail. So it's not a nice picture or yet another map. It is indeed something that takes us down to individual villages, individual communities, and become very useful not just for a water manager at river basin scale, but to the individual smallest administrative level here. Now another example which adds yet another dimension that we were missing in the previous examples that I showed to you on monitoring and assessment indicators. Here this shows us the catchment again and the differences in water tables between the climate scenario of 2051 to 2060, a 10-year period, and a reference period where there are monitoring data available from 1991 to 2000. The change in meter, in this case the red part here, all the red boxes indicate a decrease in water table compared to the reference period, and the blue suggests an increase in water table compared to our reference period. And this is now very interesting to see how these different stretches of the river, where we don't have an aerial coverage, we have stretches of the river or river systems where we can see how water tables will be negatively impacted, other parts where the water table will see a positive impact, and then we have an aerial coverage for some of those where we see in larger parts affecting subcatchments, watersheds with negative impact, large decrease in, or fairly large decrease in water table. And then we have other watersheds here where we would expect an increase in water table. So there might be different reasons for this to happen. And it's in all of the cases that you can see here, you can get additional background reports to it. You don't have only the maps and where you can click and add or visualize additional baseline data, but you can also click through the system and obtain additional reports that were produced for each of these maps. So the map is just an interface which gives us sort of an output, a final product. But still, as a user, we have access also to the more detailed scientific background linked to it. In this specific case, the white areas are areas where this groundwater model was not active, and for that reason, this calculation could not be done. Now, let's move to the third part of our options of assessing sustainability, the systems thinking, which leads us to the restructuring of existing systems. Let's think of the hydrological systems. And as any other system, the hydrological systems are characterized by an intrinsic capacity of self-organization, of resilience, and of construction of hierarchies. Those are typical properties of a system. And if you break a part of the system away, it is capable of restructuring itself and being able to recover or to work on and function as a system fully with all of the capabilities. And then we have a system only if there are hierarchies in place. Now, the systems approach is important because we can understand river basin management better when we use that frame. So remember what we talked about earlier when I introduced this concept to you, that the system's components are stocks, flows, feedback loops, and information communication flows. And we talked about these stocks and flows earlier. What I want to focus on now is slightly different. I want to focus on feedback loops and attach to the feedback loops on traps. I recommend you very warmly to get hold of this book here, written by Meadows, Thinking in Systems. It is very helpful to understand systems functioning, and also very useful to help rethinking how river basin management can be done. And with this, I want to leave you now and come into the systems thinking in more detail next time.